All right, we're going to take a look at our worksheet from last night, questions 8 and 9 that we had for homework. Real quickly, I'll just go through these real quickly, okay? And as much as these might be kind of difficult to draw the diagrams, kind of difficult to actually solve sometimes, once you see them done, the mathematics of these ones are really, really easy, really, really quick. They're actually shorter than some of the other questions, just a little bit tougher to draw them. The first one, question number 8, said, the captain of a ship wants to go directly north. Wants to go directly north at a speed of 35 meters per second. Right away, we know that's going to be a dotted line vector. He wants to go directly north at 35 meters per second. But there's a current to the east. Okay, we don't know what the value of that current is to the east. We just know that it's to the east. It says the speed of the boat without the current would be 50 meters per second. What's the speed of the wind? Should say what's the speed of the current, I guess, right? We're going to draw that current over here so that our dotted line vector is going to be drawn start to finish. That current is going to be drawn right there, but we just don't know what its length is yet. That third vector is going to be drawn right here so that it's drawn front to back with the other solid line vector. Now that third vector, it tells us the speed of the boat without the current. In other words, the speed in still water. Okay, the speed if there was no current whatsoever, 50 meters per second. That's a solid line vector as well. Well, we know it's not this one because that's the current. We know it's not this one because that's the dotted line vector. So this one must be the 50 meters per second. We want to solve for this one right here. We want to solve for the speed of the current. Now, it's a little bit different than the other problems we've done because we're not looking for the hypotenuse here. But it's still the same equation. We know that the Pythagorean Theorem applies where a squared plus b squared equals c squared. But we're not looking for c squared. We're looking for a or b. So let's say, let's just call it question mark. Okay, whatever we want to call that. That's the current is going to be equal to the square root, not of 50 squared plus 35 squared, but rather 50 squared minus 35 squared. Okay, again, instead of solving for c, a squared plus b squared equals c squared, we're solving for a. A squared is equal to c squared minus b squared. We do the math on that one, works out to be 36 meters per second. So what's the value of the river current here? What's the value of the river current? 36 meters per second. How many people got that? Good, good, excellent. Question number 9, similar question. It says a pilot of an airplane wants to fly directly west to Vancouver. Wants to fly directly west to Vancouver. We know that that's going to be a dotted line vector. We just don't know what its value is yet. But we'll draw it as a vector to the west because we know that we are trying to fly directly west. There's a wind blowing to the south at 25 meters per second. Let's draw that in here. Wind to the south at 25 meters per second. Okay, that's drawn correctly because, again, we know that dotted line vector has to be drawn from start to finish. In other words, there's going to be a head-to-head there, or front-to-front. The airspeed of the airplane is 100 meters per second. The airspeed, that means the speed if there is no wind, is 100 meters per second. Well, we know that other vector has to go up here so that it's drawn front to back. Okay, we know it's a solid line vector because you can't have two dotted lines. Two solid lines got to be drawn front to back. So we know that it's drawn up there. And we're told the airspeed of the airplane is 100 meters per second. That's not a resultant vector, so it must be that third vector right here that we just drew. We're looking for the speed that the plane actually travels. Okay, so we're looking for this speed right here. Just like in the other question, we were solving for a variable that wasn't the hypotenuse, we're going to solve for a variable that's not the hypotenuse here either. In other words, we're going to solve for a. Instead of a squared plus b squared equals c squared, we're going to say a squared is equal to c squared minus b squared. In other words, v is equal to 100 squared minus 25 squared. We do the math on that one, and it's going to work out to be 97 meters per second. How many people got that one? Less people got that one. Okay, but still not bad. You guys feel okay about those? Okay. I'll tell you that setting up the question on your quiz on Monday will be a little bit easier than question 8 and 9. Mathematically, it's not going to be any easier. but setting it up in terms of the vector diagram would probably be a bit easier. All right? Now, we also had a couple of other questions for homework on page 107. Those related to projectile motion. We'll spend just a couple of minutes reviewing that stuff, and then we'll go back and we'll check over these two questions. You guys remember that a projectile is anything that moves through the air under the influence of just gravity. Nothing else. No air resistance, no force due to a person throwing it or whatever. Okay, once it's released from our hand, it's a projectile. While it's in our hand, it's not, because we have forces other than gravity acting. We know that if a projectile is launched off of, say, the edge of a building or off the edge of a cliff, it's going to take a path that looks, Travis, something like this. Does anybody remember the name for the shape of that path? What is it? Good, thank you. It's a parabola. Yeah, parabola you guys have learned about in math class. Remember, 0 is equal to a squared plus b squared plus c. You guys remember that? The equation for a parabola? No? All right then. Doesn't matter. Doesn't really matter. I know one of you remembers it at least. It is a parabola. In fact, it's only a half a parabola, because the full parabola would go back like this, right? But we still call it a parabola. The height of this cliff, or the height of this building, or whatever it is going to represent a displacement. But this is also going to represent a displacement. How far from the edge of the building or the base of the building or cliff that it lands. What's the difference between those two displacements? They're not the same value because one's x and one's y. Right? What's the difference? I just said it. One's an x and one's a y. Because we've got two different components, an x and a y, we have to separate them. What equation do we always use to describe the x component? No exceptions, every single time. Nick, you remember this one? No? Oh. Careful there. Not delta V over delta T. Delta D. Maybe that's what you said. Delta D over delta T. Every single time. There will be no exceptions to that. Even if you go on and take engineering in university and you do a projectile motion question, which you will if you take engineering in university, I guarantee you, you're going to use this equation to describe the x component. No matter how complicated the question is, no matter how much more detailed it is than what we're doing right now, you will still use that equation to describe the x component because it's constant velocity horizontally. It's not speeding up or slowing down on the x-axis. Now, the y equation, we can use any one of a number of equations for that because it's accelerating. We use any of the group B equations, but the one that I suggest that you always start with, only because, not because it's better than the rest of them, but because it's the one that works more often. The one that we're always going to start with, D is equal to VIT plus 1/2 AT squared. Now the strategy, or the lack thereof, is simply plug numbers in. Whatever numbers you got, put them into one of the equations. Okay, put them into the appropriate equation, and then get something. Okay, it doesn't matter if you get what you're looking for right away, that's great. Stop. You're done. If you don't get what you're looking for right away, that's okay. Just keep working. Just keep plugging things in and try to get something. If you get something other than what you're looking for, great. That provides you with another piece of information that maybe can help you to get what you're looking for. One final thing before we take a look at those two questions. V and VI are two different values because one's x, one's y. Delta D are two different values because one's x and one's y. A, well, there is no A in the x component because it's not accelerating. So A would be 0, I suppose you could say, for the x component. A is neg 9.81 for the y component. Two different values because one's x and one's y. T, on the other hand, for the x and the y, are the same values. Why can we do that? Why can't we say D is the same for both x and y, V is the same for both x and y, A is the same for both x and y? Why can't we do that, but yet we can say that T is the same for both x and y? Travis? Good, because t is a scalar, v, d, and a are vectors. Good. All right, we had three questions for homework last night, although we actually did question number 1 in class yesterday. Okay, I'd like to take a look at number 2 for sure, and then if you guys want, we can also take a look at number 3. It just depends on how question number 2 goes for us, okay? Number 2 says, an arrow is fired horizontally with a speed of 25 meters per second from the top of a 150 meter high cliff. Here's our arrow. It's launched with a speed of 25.0 meters per second. And it comes down and it's going to hit the ground somewhere. How long does it take to come down and hit the ground? By the way, the cliff is 150 meters high, right? How long does it take to come down and hit this ground? Oddly, it's a 3-word answer. I don't know. We don't know how long it takes to hit the ground. We're given a time here of 2.5 seconds, but that time, we're not given the time that it takes to go from here down to the ground. Okay? We're told that it falls for 2.5 seconds. Okay, so maybe it gets to this point in 2.5 seconds. We want to know how far it's fallen. In other words, if we want to know how far it's fallen in that amount of time, 2.5 seconds, this 150 meter distance that was given to us, the height of the cliff, is really not relevant at all. We're told that that's the height of the cliff, but we're not told that it falls all the way down. It will fall all the way down, but we're not told that it falls all the way down in 2.5 seconds. We want to find this number right here, the displacement on the y-axis right here. The 150 meters is completely irrelevant in this question. It's thrown in there just to see if you can recognize that it doesn't matter. Rutger? No, the 25 meters per second wouldn't be irrelevant. It's a good question, but it would absolutely be relevant because it's falling for 2.5 seconds. We don't know where it ends up right now, at least after 2.5 seconds, but we do know where it started. Okay, we know that it started at the top of the cliff, and we know that it started with a velocity of 25 meters per second. Okay, so it is relevant. It's a good question, but it is relevant. Okay, let's break it up into our x and y components now, remembering that delta D is not 150. That 150 is not a relevant number to us. X component, always described by the equation v equals d over t. The y component, usually described by the equation vit plus 1/2 at squared. Let's plug numbers in. Okay, see what we can get out of it. We're looking for this number, right? We're looking for how far it falls vertically in that time. But don't worry about that right now. Just plug numbers in where they fit and see what comes out of it. V is 25 meters per second. D, we don't know. T, we do know, 2.5 seconds. That allows us to solve for delta D, x component. We end up getting 62.5 meters there. Is that my answer? We said we're looking for D, right? Is that my answer? Yes, that's how far it travels horizontally. That's not my answer. That's correct, but it's not my answer correct. Let's do the y component. Looking for delta D here. Can you tell me what VI is for the y component? 0. That 25 meters per second is all horizontal, none of it downwards or upwards. So we'll just cross that off. 0 times t is 0. A is negative 9.81, and t is 2.5. We got to square that. 2.5 squared times 9.81 times 0.5 is 30.7. It's actually negative 30.7 meters. That's my answer. How far has it fallen? Well, the displacement is negative 30.7 meters. We're actually asked for the distance, so technically it becomes a positive value because distance is a scalar, right? You leave it as negative 30.7 though, and I'd mark that right. Rutger, after I solved this, actually, I think I realized a little bit more what your question was, Rutger. Rutger said, is the 25 meters per second initial velocity irrelevant as well? Okay. In a sense, Rutger, you're right. It is irrelevant in the sense that you don't actually need the value to get the 30.7, right? We solved the x component. Turned out we didn't need to do that. So it's not relevant in that sense. You're right. But it is a number that's valid. Okay? It is a number that's valid with this problem. It just doesn't help me. Okay, the 150, we said, wasn't relevant because it has no bearing on the question whatsoever. It's not even valid for the question because it doesn't say that the object falls that far. Does that make sense, the difference between those two? How they're both not relevant, but one is perfectly valid, just doesn't help us. Okay, the second one is just not even valid. You okay with that? How about question number 3? Do we need to go over that one? Do you want to go over that one? Yes? Okay. 3 says, what's the horizontal speed of an object if it lands 40 meters away from the base of a 100-meter high cliff? Here's my 100-meter high cliff. It lands 40 meters away. What's the shape of that path again? It's a parabola, right? They are a half parabola. We want to know what this speed is up here. X's and Y's. Nick, I know you know this time. What's the equation that we're always going to use to describe the x component? Good. Excellent. V is equal to delta D over delta T. Good. Every single time. Okay, no exceptions. So let's make sure that we have that down pat. The y equation, we don't have to try this one, but it's the one that works the most often. Let's try VIT plus 1 half ET squared. Strategy? It's a pretty loose strategy. Just plug in numbers and see what happens. Do we know what V is for the x component? We don't. Do we know what D is for the x component? What's D for the x component? 40 or 100? Good, 40. We don't know what T is, so that didn't seem to be overly helpful to me, at least not yet. But that's okay. Okay, I didn't do anything wrong. Just didn't accomplish anything yet. Do we know what D is for the y component? Do we know what D is for the y component, Brendan? Good. Negative 100 because it's down. VI is 0 because it's all horizontal. It tells me we're looking for the horizontal speed. A is negative 9.81. All right, we can get T here. We weren't necessarily trying to get T, but we can. Okay, let's solve this here. We're going to say negative 100. Let's divide that by 0.5. Let's divide that by negative 9.81. Let's square root that now to get T. We end up getting 4.5152 seconds. What am I going to do with that time now? Question's easy now, right? Question's easy now. What am I going to do with that time? Time can go back and forth, right? So, Laura? Yes. Good. 40 divided by that time, 4.5152 seconds equals, I assume, 8.86 meters per second. Good? Good with that? They're not so bad, hey? Once you kind of get the hang of it, you know, sometimes you're solving for the y displacement, sometimes you're solving for the x displacement, sometimes you're solving for the velocity, but in the end, the problems are still really all the same. It's just kind of rearranging, solving for a different variable, that's all. Okay, the next type of problem that I'm going to give you is still projectile motion, but it's slightly more complicated. Not much, but slightly more complicated. It's probably a little bit more realistic, though. Things can be launched horizontally off the edge of a building or off the edge of a cliff. But oftentimes, they're not. Oftentimes, they're kicked at an angle. It's a football that's kicked at an angle, or it's a soccer ball that's kicked at an angle, or it's a baseball that's thrown at an angle, or it's a golf ball that's hit with a club at an angle. What's the shape of that path going to be? Well, this time it's going to go up, and then it's going to come back down. What's the shape of that path? It's still a parabola, except this time it's a full parabola instead of a half parabola. Now, you're going to normally be given the initial speed here. Let's say it's 10 meters per second. Let's say it's at an angle of 30 degrees. We're going to do the same basic thing as we did for the last set of questions. It's just going to look a tiny bit different. We're going to break it up into x's and y's, and as Nick knows, the equation that we're going to use for the x component is? Good. Still the same. Okay, just because the problem looks a little bit different now when we're launched at an angle here, we still use the same equation for the x component. And, in fact, we're still going to use the same one for the y component. 1/2 at squared for the y component. Now, remember for that last set of questions. For the last set of questions, all of the velocity that was initial was x. Now it's not. Some of that 10 meters per second is x, some of it's y. How do we figure out how much of it's x and how much of it's y? You guys know this. Okay, we haven't done it in this context, but we've done it in other contexts. Fraser? Yeah, yeah. Basically, we say to ourselves, we don't like funny angles, so we got to get rid of it. Let's draw it off to the side over here. Let's say cosine 30 degrees is equal to x over 10. X ends up being equal to 8.66. Sine 30 degrees is equal to y over 10. Y ends up being equal to 5.0. Now, let's go back into those two equations and follow the same strategy that we did yesterday and earlier today when we were going over our homework. Plug in numbers. See what happens. What's v? What value of v do I plug in there? 8.66. Remember, in the last set of questions, it was whatever value you were given because it was launched horizontally. All of it was x. This time, that's not the case. We've already found the x component. It's 8.66. It's equal to delta d over delta t. Well, that wasn't helpful because we don't know what d is or what t is. Here's one for you. What's delta d for the y component in this problem? No, it isn't. No. vi is 5, but not delta d. Fraser? 0. Why is it 0? Hayden's nodding his head like in agreement here. Why is it 0, guys? Yep. It starts here. Where does it end? Vertically? Right here. It ends up at the same height that it started with. Now, d for the x component isn't 0 because it goes from here to here. But for the y component, it's 0 because it starts here and it ends here. So we're going to say d is equal to 0. That makes life a lot easier for us. What's vi? 5, right? The y component, it's 5. Now, remember, the x component will stay 8.66 through the whole problem. The y component won't. It's going to change as it goes up into the air and comes back down. That's why it says vi instead of just v. All right. We've got one unknown there. It's t, but it's not pretty to solve for. Let's simplify this a little bit before we actually try to solve it. It's going to be 5t minus 4.905 t squared. Where did that 4.905 come from? Yeah, half times 9.81, right? And it's negative because it's negative 9.81. Now watch what I'm going to do here. I'm allowed to do whatever I want to this equation as long as I do it to every term in both sides. I can divide every term if I want by 16,145. I can do that. I'm not going to do it because it's not going to be helpful to me, but I can as long as I divide every term by 16,145. It's more convenient, yes, to divide everything by t. Zero divided by t is 0. 5t divided by t is 5. 4.905 t squared divided by t is 4.905 t. Well, now it looks a lot simpler, right? T is only in one place. Let's take the 4.905 to the other side by adding. It becomes 4.905 t equals 5. T is equal to 5 over 4.905. Gives me 1.0194. 1.0194 seconds. It's no different than the other problems now, right? Let's just take this time. Time can go for in between x and y, right? So let's just say 8.66 is equal to delta d for the x component over the time of 1.0194. 8.66 times that. We end up getting 8.83, or 8.8 meters. How far does this ball go? You kick this soccer ball at this angle of 30 degrees, 10 meters per second. How far does it go? 8.8 meters. Does that make sense? What's the same about this question versus what we did yesterday? Almost everything. What's different about it? Well, this is different because v was the number that was given to us. Now we have to separate the x and the y. Similarly, this was 0 for all the problems that we had yesterday. Now we have to separate the x and the y from the initial velocity. Finally, this will be different. Yesterday, delta d was always a negative number because the object always fell from the edge of a cliff or from the edge of a building. For these questions, d is always what? 0, because it lands at the same height that it started. Other than that, this question is exactly the same as what we did yesterday and what we did for homework last night. Does that make sense? You guys feel like you need another one of those, or do you feel okay with that? That's a good question. That's a really good question, Travis. You kick a ball off the edge of a cliff like this. That's still a parabola. Okay. That's still described by x and y components. It's still described by the same equations, but there's only one person in this, two people in this room, including myself, that would be able to solve that question. Laura and me. Why? And maybe you. Have you taken Math 30 yet? Yes. So you probably could too, because you've done the quadratic equation as well then. So 3 of us in this room that could do that. Why? Because in the end, delta d for the y component there would not be 0. So delta d would be, say, neg 10 or whatever. Let's say vi was 5. Yes, okay. Yeah, if you were given the time, then absolutely you could do that. Absolutely. Without doing the quadratic equation. If you're solving for the time here, like we do most times, you can't solve for t there. Most of us in this room can't solve for t there. We have no idea how to do that. It's not just standard algebra. You need that quadratic equation to do that. And again, most of you have never even heard of it, let alone used it. So we won't get a question like that unless, you made a good point there, unless we were given the time and we didn't have to solve for time with the quadratic equation. Okay? So you guys okay with that as an example, or do you want another one here? Again, what's different? We just had to break it up here, right? Into x and y. Plug the x into here, plug the y into here, and then make sure you make this one 0. Then treat it exactly the same as the other question. Do you want to just stick with that and see if we're good? Try a couple practice problems. If we need to revisit it and go back later on, we can. Okay, what I'd like you to do then is questions. Just let me check and make sure these are the ones that I meant to assign to you, okay? All right, you guys, there's one question that I was thinking of that isn't there, and I'm not sure exactly which page it was on. I've kind of a little bit lost track of it there in my notes there. I'm going to add one question to this, okay? Okay, I want to add one question to this. I want you to do both of these, but I'm going to add a question number 3 on there as well, and then that's where we'll wrap it up for today. Okay, I want to say a ball is kicked. You can do these in any order, by the way. I don't care whether you do them in this order or not. Make this number 1, make this number 3, make it number 2. I don't care. A ball is kicked from ground level to ground level. In other words, it ends up exactly where it started on the y-axis. At an angle of 30 degrees. And a speed of 20 meters per second. I want to know how far the ball goes. How far does the ball go? All right? So do these 3 questions. Because I'm adding one to it, I'm going to give you a little bit of a break. And I'm not going to ask you to solve question 2C. We'll talk about that a little bit on Monday, okay? Questions 1, 2A and B, and then this new question, 3. All right? You can get at it. Use the rest of the class to work on these. Ask me some questions as you happen.